So you're used to testing simulations, software testing, right? You apply different inputs, okay, and you look at the output, okay, the actual output coming out of your software simulations, okay. You compare this guy with an expected output. Okay, we compare the actual output of simulations with the expected output of the simulations to tell you if they tally or not, if the circuit is functioning the way it should function. Okay, and once you test on schematics, you do your layout, you extract your layout, and you do some more simulations on that. You apply the same set of inputs, you look at the output, okay, you look at the output and compare that to the expected value. Okay, what is it that you expect? Okay, and then to see if they match. If they match, then if they match for all possible input combinations, then your circuit is functioning properly across all the. Then there are different kinds of. There are more. There's some more testing that you can do. Corner analysis, so on and so forth. You look at the operating corners. What's the worst that can happen? The worst case simulations. Okay, so you look at all of those kinds of software simulations. This chapter is more about hardware testing. Okay, so you're looking for faults, or this provides a methodology to test for faults after manufacture. So this is in contrast to the software testing that you do before manufacture. So this chapter is all about testing after manufacture. So typically, let me talk about the situation you find yourself in after manufacture. You have a chip that has certain input ports, okay, and you have an output port or a bunch of output ports. Okay, you have a set of inputs, you have a set of outputs, and that's about it. You don't have access to a lot of internal nodes. Okay, so you have to limit yourself to what's known as a black box testing, where you only have access to a set of inputs and a set of outputs and not to the internal nodes. Okay. On the other hand, when you're doing your software testing, you can annotate the internal node voltages and see the exact voltages at different nodes, the currents flowing through each of these branches. You can analyze the circuit. You can take a look in the internal conditions of the circuit. Not so, you cannot put a probe into the internal nodes of an integrated circuit after manufacture. So you find yourself in a slightly different environment. You find needing a set of different skill set, okay, that correspond to black box testing. So this idea corresponds to the notion of design for testability. Okay, where you pay attention to designing your circuits upfront in a manner that lends themselves to easy testing. Okay, so how can you design circuits so that they're easy to test after manufacture? So that is the consideration of testing after manufacture. Okay, so now when you're testing a combinational or sequential circuit, so when you're testing a combinational or sequential circuit, your analysis or your testing methodology becomes very convenient if you note the fact that the manufacturing faults, also called defects, in sequential or combinational circuits can take the form of some kind of short circuits or some kind of open circuits. Okay, for example, let's say you have a simple AND gate with two inputs. Okay, what do you think happens when one of the inputs is shorted to ground? Well, then what happens is, then this input is going to be permanently stuck at zero. So independent of what you're trying to put. So let's say you're trying to put a 1 and 1 on this node. That doesn't matter, because of this short, the output is always going to be 0. Okay, so that's the kind of faults that are possible in hardware, and these faults creep in during manufacturing time more often than you think. Okay, so a very good technique to test them is known as fault modeling. Okay, where you use the idea of stuck-at faults. Okay, and then it's easy to see that one of the inputs here, this guy, is stuck at 0. Okay, so it does not respond to the inputs and changes of the inputs in a way that you expect it to. Okay, that's a fault. Okay, so in order to understand how this is advantageous, let me show you an arbitrary combinational circuit. Okay, let's say I want to pick an arbitrary combinational circuit, something like this. Okay, I'm just making this circuit up. Each of these has 3 inputs: A, B, C, D, E, F, G, H, I, J, K, and L. Okay, and then I don't know, let's say this guy goes to some kind of NAND gate, XOR gate. Okay, and then let's build a NAND gate over here. Okay, so the idea is, if you have a combinational circuit with number of inputs all the way from A through L, that's 12 here in this case. Okay, so how would you go about testing this circuit if you follow the regular brute force approach? The brute force approach is based on the truth table. Okay, you start with the very top row in the truth table, which is all zeros. Okay, and you look at the expected output. Okay, you look at the expected output, and you look at the actual output. And if they tally, you conclude that for this particular input condition, it is verified. And then you continue so on and so forth, all the way until you exhaust all the possible input combinations. And then you expect, and then you tally the expected and the actual outputs. Okay, and when you verify that they are accurate, when they match, you know you have fully tested this circuit. But what do you think is the disadvantage of this circuit, of this kind of testing? Let's see, something in the chat window. Okay, time consuming, that is correct. Alberto Andrade says it is time consuming. The brute force approach, if you think about it, you need 2 to the 12 different tests, starting from this guy to this guy. Okay, that's how many, a battery of tests that has to go through each of the input possible sequences. Okay, so this is the brute force approach. Thankfully, there's a much more clever, much more efficient alternative that is based on the idea of fault modeling. Okay, so let me copy this to illustrate the notion of fault modeling. Okay, like I mentioned, the possible faults could be shorts or open. Okay, so if you take any node, does not matter, any node, it could be shorted to ground or it could be shorted to power supply. So any node, the possible fault, so let's name them as M, N, P, Q, R, S, T, and let's call this guy as output X. Okay, so if you look at node M could be stuck at 0 or stuck at 1, and I'm going to represent them as M0 and M1. These are the only two faults that are possible at node M. Even so, node N could be stuck at 0, or it could be stuck at 1. That's about node N. Same thing with node P. P could be stuck at 0, P could be stuck at 1. Q0, Q1. So what I'm doing here is I'm attempting to list all the possible faults. Okay, R could be stuck at 0, R could be stuck at 1. The same thing with, and this is the same thing as R, right? So I don't want to duplicate those. S, this guy is S. Okay, so S could be stuck at 0 or S could be stuck at 1. The same with X, could be stuck at 0, X could be stuck at 1. And the exact same thing for A, B, and C, A through L. Each of these 12 inputs could be stuck at 0 or they could be stuck at 1. So if you count the total number of faults possible, that comes out to be 7 plus 12, 19. So a total of 38 possible faults. So this guy is an exhaustive list of all single stuck-at faults possible in the circuit above. Okay, so what I have done in an attempt to outperform the Alberto had the question, if R and S are the same nodes, they're the same nodes. I fix that. So in an attempt to outperform the brute force approach, I am relying on the notion of stuck-at fault, okay, or fault modeling, which looks at each node and tries to eliminate if there's a stuck at 0 or a stuck at 1 at each of those, right? So that's the idea of stuck-at fault modeling. So if I can do that, it all comes down to just 38 possible tests. Okay, so if I can use 38 is the exhaustive number of faults possible. So if I can use 38 input patterns to test, compare that to the 2 to the 12 test patterns needed using brute force. So this guy is brute force, right? And this guy is fault modeling. Okay, so that's quite a significant advantage. 38 versus 2 to 12. Okay, and then the idea of fault modeling is based on the notion that at any given node, there's only two possibilities that can happen. This guy could be stuck at 0, or this guy could be stuck at 1. So if I test for these two faults, then I have completely tested that node. Okay, then I go on to test the next node. So if I can test for the presence of a stuck at 0 or a stuck at 1 at each of the possible nodes, then I have thoroughly, completely tested my circuit. That's the idea of stuck at fault modeling. Okay, and then I'm going to illustrate what you have to do to test for stuck at faults at a particular node. Okay, with an example. Questions so far, please? Okay, so let's take this idea of stuck at fault modeling a little further. Okay, with an example. Okay, stuck at fault modeling. With an example. Okay, so let's see, let's draw a simple example of AND gate here, of a combinational logic circuit here. It is an AND gate followed by OR gate. Okay, followed by another AND gate, and then by OR gate. So this is OR, this is AND. Okay, let's name them and illustrate how to do the stuck at fault modeling. So I'm going to call this A, B, C, D, E. These are the inputs. Okay, so if you think of this as a black box, the inputs A, B, C, D, E are available outside, and the output is available outside. So this guy, call it F, that's the external output. Okay, the other nodes, these guys, okay, M, N, and P, these are internal nodes. Okay, these are internal nodes. Now, let me illustrate the idea of stuck at fault modeling. Let's test for N stuck at 0. Okay, I said I want to test for N stuck at 0. First of all, let's list the exhaustive collection of all the faults possible. A could be stuck at 0, A1. Then comes M internal nodes, N0, N1, P0 and P1, and also F0 and F1. Okay, so this is the exhaustive list of faults that is possible in my combinational circuit. Okay, good. Then if I can test for the presence of all of these faults, then I have thoroughly tested my combinational circuit. So let me start by looking at n stuck at 0, which is n0 fault. Okay, that's the fault I'm interested in testing. Okay, it's an interesting concept. Let's see how I go about testing that. How can I test if n is stuck at 0? Okay, that's this node stuck at 0. Okay, n stuck at 0. So I'm going to represent 0 here as a fault. In order to test that, I try to put a 1 on this guy. Okay, that's called excitation. So in order to test for n stuck at 0, we first need to excite by trying to make, let me be accurate here, by trying to a 1 on n. Okay, so this is the no fault value, and this is the faulty. This is what the AND gate sees if it is indeed stuck at 1. And this is the one I'm trying to put on it, 1. So in order to make this a 1, okay, what value do I have to pick for A? I make a value A equals to 1, B equals to 1, and C equals to 1. So if I pick A equals to 1, B equals to 1, then this guy becomes a 1. And if I make this guy C also equals to 1, then I accomplished in putting a 1 on that node. Okay, so the first step in stuck at fault modeling is to excite the particular fault by trying to put the opposite of the fault. The next step is to propagate. Okay, in order to propagate this fault, what I have to do is to put a 0, no, not a 0, I have to put a 1 on this node on D. Okay, if I try to put a 1 on D, then what happens is, in the absence of a fault, 1 and 1 gives me a 1. And if n is indeed stuck at 0, then P is going to be 0. Okay, then what value do you think I should put on E in order to propagate this further through F? Jack Lambert said he wanted to just make C a value of 1 and not care about A and B. Sure, you could do that. Okay, in here, I chose to make a value of A is 1 and B is 1 and C is 1. Okay, so let's see, my claim is that I want to put a value of 0 on this guy E, because in the absence of a fault, this 1 and a 0 over, or a 0 over here, the or of those two will give me a 1. In the presence of a fault, 0 or 0 is going to give me a 0. So what I have done is to pick a value of A equals to 1, B equals to 1, and C equals to 1 in an effort to make n equals to 1. Okay, then in an effort to propagate the fault, what I have done is to make D equals to 1 and E equals to 0 in order to propagate. Okay, 0 for E, correct. Okay, in order to fully understand the rationale, Okay, let's see what happens if instead of picking a 0 on E, I end up picking a 1 on E. Does it still work? Does the approach still work? Or what is wrong if I try to apply if I try to apply a 1, okay, on E? How is it going to be a problem for me? We wouldn't see the value of P. That is correct. So because this 1 is sitting on the input of OR gate, in the absence of a fault, it's going to show up as 1 because 1 ORed with 1 will give you 1. In the presence of a fault, you would still see not a 0, but 1. Okay? So in other words, if you apply this input, 1, 1, 1, 1, 1, and look at the output, in the presence of a fault and in the absence of a fault, it's going to be the same. Okay. However, if you put a 0 on here, then no fault scenario is going to be 1. Okay. And then the faulty scenario is going to give you a 0. So in other words, by looking at the output, you want to make sure that the no fault output and the faulty output are different. You want them to have different outputs. Okay, so that's the idea of propagate. You don't want to camouflage. And Alberto has the right idea. We won't see the value of P on the output. Okay, correct. So we're trying to see propagate this value in the presence of a fault and put this value in the absence of a fault. That's exactly what you should see here. In the absence of a fault, you would want to see a 1. In the presence of a fault, you would want to see a 0. So in order not to camouflage that output, you want to make sure you pick a value of 0 here. Okay, let's do another example here. Okay, let's pick another value. Okay, let's see. Let's arbitrarily pick, I don't know, this is M, right? Let's arbitrarily pick any particular node, any node, and then see if we can test for a fault on this guy. I want to test for P stuck at 1. Okay, testing for P stuck at 1, which is also shown as P1. In order to do that, like I mentioned, there are 2 parts to it. There is an excitation part. And in order to excite the fault, you have to select the inputs that precede this node. And then there is a propagation part. There is an excite part. There is a propagate part. Okay, so we are testing for P stuck at 1. So in the presence of a fault, this guy should be 1. So our effort in excitation should be to put a 0 on there. In order to put a 0 on there, I can simply make this value to be 0 and then pick any arbitrary value for A, B, and C. Okay, so if I pick A equals to 0, B equals to 0, C equals to 0, and D equals to 0, okay, then assuming there are no other faults so far, then we have excited. We have excited a value of 0, which is trying to put the opposite of what we are trying to test. Okay, so in order to propagate here, okay, we want to be sure to put a 0 on this node. If we put a value of E equals to 0, then In the absence of a fault, I would see a value 0. And in the presence of a stuck at 1, we see a value of 1. Okay, so this guy, in effect, 0, 0, 0, 0, 0. This is for A, B, C, D, E. This value is called the input test pattern. And this input test pattern tests for P stuck at 1. Okay, so by applying an input of 0, 0, 0, 0, 0, you look at the output. If the output is 0, then there is no fault at P. If the output is 1, it is possible that P1 fault is present. Okay? Questions, please. What questions do you have? Okay. If you don't have questions, let me ask you a question. What do you think is the overhead? What do you think is the problem or the clear? It's clear, it's easy to see the advantages of this guy, right? You have far fewer number of input test patterns that you have to apply to look at the output to verify if your circuit is fully functional or not. Now, what I want you to think about is what is the disadvantage, or the not exactly a disadvantage, but an overhead. What is an overhead in trying to use this technique of fault modeling? You understand the notion of fault modeling, correct? So you list all the faults possible. Let me go back here. So A0 through F1, this is the complete exhaustive list of all the faults possible. Okay, then you go about eliminating each fault. Is this fault present? What input do I have to apply to test for this fault? So on and so forth. If you completely test for all the possible faults, stuck at 0 or stuck at 1 fault, then you have completely tested the circuit. In most cases, that is going to be far fewer number of tests than the brute force. That's the idea of fault modeling. What if the test inputs are also faulty? Sure, that's one scenario that you have to take into account. And that would manifest as A stuck at 0, B stuck at 0, A stuck at 1, B stuck at 1. So when we include that in our list of faults to test, sure enough, we can test for that. Okay, and as a matter of fact, I'll show you an example of how we can do that. But that's a good consideration. And that's the reason why I have included A0, A1 when we are testing for all the possible faults, okay, to see if the inputs are faulty. What other, so my question is about what is the overhead here? What is the overhead that is hidden, kind of involved in using the fault modeling approach? Okay, think about this idea along the lines. I mentioned that this test pattern 0, 0, 0, 0, 0 corresponding to A, B, C, D, E. I mentioned that this is useful in testing N stuck at 1, right? But I don't have this knowledge a priori. I have to kind of find out. I have to generate this test pattern. Okay, so in other words, I have to start with each node, a particular node n, for example, okay, and then choose a fault that I want to verify there, n1, then excite that fault, or back propagating the opposite of the fault, and then the next step is to propagate. Okay, so I have to follow both of these steps, excite and propagate, for each of the nodes and for each of the faults. So I have to do the same thing for n0 and n1. Here I have to do m0 and m1. So the overhead is that for each fault that I want to test, I have to do the excite and propagate steps. That ritual of excite and propagate over and over again for each of the faults to test.
So,
Okay?
Dr. Mallory, so what you're saying is the overhead will be that you need to test like 38 times, because that it will include all the inputs and all the nodes. Is that the overhead that you're talking about?
No, the number of tests is still going to be 2 times the number of nodes. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number of tests needed is going to be a maximum of 18. Okay, but the overhead is, let's say, hold on, let me illustrate with the example of 12 inputs, right? They go all the way from 0, 0, 0, 0, 0, 0. So using the brute force, you start with this guy and then do this. Then you apply this input. Then you apply the next input, right? And you do the exact same thing until you hit. Correct?
Yes.
So that's a total of 2 to the 12 tests, right? Now, earlier I mentioned that instead of doing that, instead of doing that guy, if I use stuck-at fault modeling, I said it is possible to test all of that using how many faults? 38, right? Using 38 input patterns. So my idea was, if I am careful in picking a select section of rows, okay, I can just pick 38 of those. So just by using 38 rows, I can simplify, right? So this is 2 to the 12 tests versus 38 tests. You're with me so far?
Yes.
Now the overhead really is which 38 rows, or how do you pick the 38 rows? Okay, which particular rows should you pick to completely test for all the faults? Okay, in order to answer that question, you'd go about exciting and propagating for each fault, right? So this idea of answering the question of how do you pick 38 rows test for all the faults. So this process adds an overhead. Okay, so just because you see an excite and propagate two sets here, you should not go ahead and multiply 38 times 2. That's not the idea. The idea is that for each of the possible 38 rows, or each of the possible faults, you would have to do an excite and a propagate step, which will eventually give you one test pattern. Okay, so to put it in other words, when you're trying to answer the question of which rows to pick, to answer that question, you have to do a lot more analysis.
Okay, so the overhead will be pretty much to do that, the excitation and the propagation, that it would take me
Yes.
time to figure out which one it is. Okay, I see.
Yes, thank you. So the excite and propagate leads you to one input test pattern, and it does take you time. You said it very well, that it does take you time to figure out the inputs A, B, C, D, and E, F, G through the excite and propagation stages. Okay, so that's a good point. Thank you for asking that question. So the overhead is the time taken, excitation, and propagation for each fault. There are a lot of automatic algorithms, automatic test pattern generation algorithms. There's D algorithm, there's podium algorithm. There's more than one algorithm that if you give a circuit, okay, they can spit out, let's say it has 4 inputs, A, B, C, D, okay? The automatic test pattern algorithms can look inside your circuit, okay, in a depth first or in a breadth first manner, and spit out all the input test vectors needed to completely test all the faults possible. Okay, so these are known as automatic test pattern algorithms. There's a variety of them. Questions, please. Questions so far. Okay, let me go back to the circuit again. Okay, so the idea is that at each particular node, you test if that node is stuck at 0, and you test if that node is stuck at 1. Then you have completely tested this node. Then you go about testing M0, M1, P0, P1, so on and so forth. You test for the presence of stuck-at faults on each of these nodes. And when you completely test for all the nodes, then you have fully tested this circuit. Does that make sense?
Yes, he does, Dr. Maduri.
Okay. Now here is an idea for you to consider. Let me copy this. I'm going to paste it here. Okay. I said by using a value of A, B, C, D, E, the values of 0, by using these values, I said it was possible to test for P stuck at 1. So let's do one more example. We'll do one more quick example, okay? And then take the idea further, okay? Let's say you want to test for, I don't know, M stuck at 0 or stuck at 1, okay? Let's test for M stuck at 0, okay, which is M0. In order to test for M0, there are two parts to that. I first have to do the excitation part, and then I have to do the propagation part. Okay, I'm testing for a fault 0, so I try to put a 1 on here. In order to put a 1 on there, I should make a value of A is 1 and B is 1. That's what makes M value 1. So excitation, as a part of that, I pick a value equals to 1 and B equals to 1. So we have arrived at 2/5, a small part of the entire input test vector that I have to apply. And let's do the next step as well. Let's propagate. So in order to propagate, I choose to apply a value of 0 on this guy. Okay, that way, in the presence of a fault, 0 or 0 is going to give an output 0 of this output OR gate. Okay, and the OR gate here is going to give me a 1 in the absence of a fault. So I kind of preserve that. Okay, now I pick a value of 1 for the input D here, so that the AND gate, this AND gate here, gives me an output of 1 in the absence of a fault and 0 in the presence of a fault, and so on. If I pick a value of E equals to 0 here, a no fault scenario is going to be 1, and a faulty output is going to be 0 for the OR gate here. So out of propagation, I arrived at values for C equals to 0, D equals to 1, and E equals to 0. So by combining excitation and propagation, I arrive at 1, 1, 0, 1, 0 as the test pattern. Okay, 1, 1, 0, 1, 0. So if I apply an input of 1, 1, 0, 1, 0 here, and see an output of 1, implies there is no fault. If an output is 0, that implies NM0 is possible. Questions, please. What questions do you have? So let me say, no fault is a wrong thing. M0, not present. So this fault of M0 is not present. If I see an output of 0 in response to an input here, input test pattern. Questions? If the output is wrong, can that mean that our fault be on another node not currently being tested? Thank you, Alberto. That's a very, very good question. Okay, so let me, his question is, if the output is, let's say I'm going to copy this. Okay, the argument I made was that if I apply an input that looks like this, okay, if I apply an input of 1, 1, 0, 1, 0 on A, B, C, D, E, and see an output of 0, and I mentioned that this could lead me to believe that M0 is possible. You have to pay attention to the fact that I was careful in mentioning that M0 is possible. I don't know for a fact. It could very well be that simply F is stuck at 0. So it is possible that M is stuck at 0, or it is quite possible that F is stuck at 0. That's possible too. Okay? Or it is quite possible that P is stuck at 0. That's possible too. So the only thing I know for a fact is if I apply this input and see an output of 1, then I know for a fact that M0 is not possible. Okay, so going back to Alberto's question, it is quite possible that this faulty output 0 is coming from a stuck-at fault M0, or it could be a manifestation of a stuck-at fault N0 there. Okay, or it could be a manifestation of P0 as well. It may not be possible for us to put our finger exactly on where that fault lies, but it is enough for us to know if along a particular path there is a stuck at 0 fault, then that circuit is useless, irrespective of where that fault is. Okay, so if the output is wrong, can that mean that our fault be on another node not currently being tested? Correct. That answer is right, but we don't care as long as it is somewhere along that path. Okay, does that make sense? Okay, so now that's also the idea that I'm going to present to you when I talk about when I say path sensitization. Path sensitization. Okay, what I mean is, let me remind myself, I was testing for M stuck at 0. M stuck at 0. This is what I was testing, right? So the same input pattern 1 1 0 1 0, as a matter of fact, can be used to test not only M stuck at 0, but also N stuck at 0. It could also be used to test for F stuck at 0. So the same input test pattern can be used to test for more than one faults. Okay, so in one shot, just by finding this input test pattern, I can eliminate more than one faults. If I go back to the list of all possible faults, I can knock out more than one faults in one shot. So that is where this technique becomes more advantageous. Okay. Questions, please. Okay. If you don't trust me, take a look at this. Okay. Let's do a fun example one more time. Let's pick a value 1 1 0 1 0. Okay. The same value that I got from above. And I said if I see an output of 0, it is possible that there is a M stuck at 0 fault present there. And if I see an output of 1, then M stuck at 0 is not present. Okay, let's use the exact same input test pattern. Okay, and my claim is that it can be used to test for N stuck at 0 as well. Okay, N stuck at 0 can also be tested. Let's see if that is indeed the case or not. Okay, so in order to test for N stuck at 0, I should try to put a 1 here. That's the excitation part. Okay, and by picking a value of 1, 1, and 0 here, I put a 1 on there. So this is 1 and this is 0. So this is in turn indeed has been excited to be a 1. Okay, and then by putting a 1 on here, okay, 1 and 1 would give me a 1 in the absence of a fault, give me a 0 in the presence of a fault. So I'm testing for n stuck at 0 using this input combination here. Okay, so you can show that in the absence of a fault, this is going to be 1, this is going to be 0. So the exact same thing. Okay, so let me prove it another way really quickly. Let's say n is stuck at 0. Okay, when n is stuck at 0, okay, by applying a value of d equals to 1, this guy is going to be 0, p is going to be 0, and E is going to be 0 as well. So 0 and 0 will give you an output of 0. So this is when, if n is stuck at 0, an input of 1, 1, 0, 1, 0 produces an output of 0. If n is not stuck at 0, then output is 1. So the same input, 1, 1, 0, 1, 0, can be used to see if there is a stuck at fault at n or not. Okay, so the idea is the same input test pattern can test for more than one fault along the same path. Okay, that's the idea of path sensitization. Questions, please. What questions do you have at this time?
Dr.
Okay.
Mituri, what is the
Yes.
difference between a test vector and a test input pattern?
They are the same. I use them interchangeably. Test vector is the same as input test pattern.
Thanks, Dr. Mituri.
Yeah. Just use them interchangeably. Other questions, please. So when you see me using the word automatic test pattern generation and the different algorithms, what they're doing is they're looking at your circuit and evaluating all the test vectors to look for all the faults in a particular combinational circuit. Okay, so if you want to test for a particular node stuck at 0 or stuck at 1, there are 2 steps to it. Okay, if you want to test for a node stuck at 0, then you have to excite it first and then propagate it. Okay, so that's the idea of combinational logic circuit testing. We'll stop here. When we come back in the next class, I'm going to talk about sequential circuit testing. That's a bit more involved. Okay, sequential circuit testing has a notion of previous state, current state, and the next state. And corresponding to that, there is a previous test value. There's a temporal difference in terms of the test vectors. So there is a sequence of test vectors. So combinational logic testing involves in test pattern generation. Okay, sequential logic involves finding a sequence of test patterns. Okay, sequence of test pattern generation. That's a bit more involved, and we'll look at that sequential circuit testing in the coming class. Okay, we have a question. Mayuri wants to find out how we can check for A or any other input. Okay, that's pretty similar to what we do in the rest of the inputs as well, rest of the cases as well. So let's do this. I'm going to copy this. Okay, paste it here. Okay, Mayuri's question is, how do you test for A stuck at 1 or stuck at 0. Okay, this is M, N, P. Okay, and she wants to find out how to test for A stuck at 0. Okay, in order to test for A stuck at 0, so the faulty input is 0, you try to put a value of 1 on it. Okay, so only this guy corresponds to excitation, and then you try to put a 1 on B. When you try to put a 1 on B, the no fault scenario is going to be 1, and the faulty scenario is going to be 0. Okay, and then you continue with the same idea. You try to put a 0 here, the no fault is going to be 1, the faulty is going to be 0. In the interest of completeness, when you try to put a 1 here, the no fault is going to be 1, the faulty is going to be 0. Put a 0 here, the no fault is going to be 1, the fault is going to be 0. So by selecting a value of A equals to 1, B equals to 1, C equals to 0, D equals to 1, and E equals to 0, you have excited the fault is 0, and you have tested it. If you see an output of 1, that's no fault. If you see an output of 0, that's a possible A0 fault. Does that make sense, Mayuri? So it's pretty similar, except that the excitation involves only one input here. Okay, other questions, please. All right, we'll stop here, and when we come back, I'm going to talk about sequential circuit testing.